Okay, I'm going to keep checking if this is recording because I have recorded this section now 3 times and it doesn't record. So what we know so far is that functions of multivariables have interesting derivatives, and in order to talk about the slope of a function with multiple variables, we need to specify a direction for that slope. So for example, we can say, when I look in the x direction, am I looking uphill or downhill? And when I look in the y direction, am I looking uphill or downhill? But you might be wondering, well, what happens if I look in this direction? Like, what if I give you a vector in this direction? How can I say whether I'm looking uphill or downhill or not? And that's exactly where the idea of the directional derivative comes in. So the directional derivative allows you to find the slope in any direction. Any direction. Like, you give me a vector and I will give you a slope in that direction. And then after we're done talking about that in this section, we'll talk about something called the gradient, which basically does something that we like to do a lot in calculus. It maximizes the slope. So it says, if you want to find the biggest slope, look to your left or something. Let me just make sure this is still recording, and it is. Okay, so the nice thing for us is that both of these things, the directional derivative and the gradient, have very simple formulas. So let me just draw this out so we can understand where this first formula is coming from. The directional derivative says, you give me a vector, and every single time it's going to be a unit vector, so I'm going to call it u. You give me a unit vector, and now remember, with vectors, one of the things that we know how to do is break this into its components. The first component and then the second component. So it's like the x component and the y component. And that's basically exactly what we use to find the slope in this direction, is multiply the x component by the x partial and multiply the y component by the y partial. And it becomes very friendly. So let's see this in action. Here's a function. I'm going to give you a particular point for this one, but here's a unit vector. Now, to just verify that this is a unit vector, remember, we just want to make sure that the magnitude of that vector is 1. So to find the magnitude of a vector, this is one of the things that we did about 2 weeks ago. We just take each component and we square it and then take the square root. And when you check this, what we get is 3/4 plus 1/4, and sure enough, that's equal to 1. So now what I'm doing is taking this vector and use it to find the derivative in that direction. So I'm going to find the derivative, the slope, in this direction for this particular function. So I'm going to take the first component of the vector, which is the square root of 3/2, and multiply it by the x partial derivative of f, the partial of f with respect to x. And then I'm going to take the second component and multiply it by the partial with respect to y. I'm just going to keep checking this because I'm so nervous it's not going to record. So now, if you have not gone through the section on partial derivatives and you haven't done the problems, this is probably a good time to stop and go back and do those, because in this section, I'm going to go through and do the partials like we are comfortable doing those, so I'm not going to explain each one every time. So make sure that you are comfortable at this point taking partial derivatives, and that we don't need to like go through each one of these. So my x component of the vector times my x partial derivative. Now in this case, the partial with respect to x is just y, and then my y component times the partial with respect to y, which is just x. So this is my directional derivative, but this is just a function right now. This is a function for my partial derivative, and you'll notice in this case we actually have a point to evaluate. So I'm going to evaluate this whole thing at the point 1, 2. So I'm going to go square root of 3/2, and everywhere I see a y, I'm going to put a 2, plus 1/2 times 1, which in the end just gets me square root of 3 plus 1/2. And that is the slope in this direction. So if I'm facing in the direction of this vector, I'm looking uphill. I can tell it's uphill because this is positive. I'm looking in this direction. I'm sorry, I'm looking up this slope in that direction. So that's my directional derivative. So now let's do another one with three components here. So again, remember, this has to be a unit vector. And in this case, it's definitely not. That vector is way too big. So big that it's going to, I mean, any size other than a unit vector is going to mess up our directional derivative. So we just are going to, I think, need to scale this one down. So let's find the magnitude of this vector. So the magnitude of the vector 2, 1, negative 2, which is 4 plus 1 plus, and then negative 2 squared is also 4. So this gives us a magnitude of square root of 9, which is 3, which tells us in order to make this a unit vector, I need to scale each component down by a factor of 3. So 2/3, 1/3, negative 2/3. And then to find the gradient, no, sorry, we're not there yet. To find the directional derivative in that direction of this function, I'm just going to multiply each of those components. So here's the x component times the x partial plus the y component times the y partial, and then plus the z component times the z partial. So again, if you haven't gone through your partials, this is a really good time to do that. So I'm going to go through and just find these partials real quick. So 2/3. Now the partial with respect to x of this entire function is just going to be 2xy plus 1/3. The partial with respect to y of this function is going to be x squared minus 3yz squared. And then the partial with respect to z of this function is going to be negative 3y. Oops, I messed up that last one. Z squared plus 1. So let me go back here. This should not be 3yz squared. I differentiated with respect to z. This should just be z cubed. Okay. Now, since we actually, this is our answer right now, but this is just a function and we actually have a point to plug in. So I'm going to plug in, everywhere I see an x, I'm going to plug in a 1, everywhere I see a y, I'm going to plug in a negative 2, and a z is going to go in as a 0. So this is going to become 2/3 for that first component times 2 times 1 times negative 2, in other words times negative 4, plus 1/3 times 1 minus 2/3, also times 1. And you can verify those things also. So when I simplify all of this, it becomes negative 8/3 plus 1/3 minus 2/3, which gives me negative 9/3. And the directional derivative in this direction at this point on this function is negative 3. So in other words, if I'm standing at this point on this function, looking in this direction, I'm looking downhill with a slope of negative 3. So that's what the directional derivative gives us. So the directional derivative is really nice because, as I said, all we could do up until this point is just find the slope in the x direction or the slope in the y direction. And the directional derivative says, well, you just point in any direction and we can find the slope that way. So it gives us a lot more flexibility with the direction of our derivatives. Now, one of the things that we like to do in calculus all the time is not just find the slope in a particular direction, we like to find the maximum of something. So in this case, we like to find the maximum slope. So that's what the gradient does for us. And the nice thing is So the gradient finds the steepest slope of the function. The nice thing is the gradient is really, really easy to find. This is the notation for the gradient. So this little upside down triangle, the gradient of f. The gradient is just a vector, and there's a lot of information given to us in a vector, and I'll talk about that in just a second. But it's the vector made up of the partials of your function. So either just the partial of x, and then partial y, or if you're dealing with a 3-variable function, you could say the gradient of f is the partial with respect to x, partial with respect to y, partial with respect to z. It could be a 3-component vector, just depending on what you're looking at. So there are 2 pieces of information hidden in this function. First of all, the direction of the vector. So the direction of this gradient vector gives you the direction of the steepest slope. The direction of the steepest slope gives you the direction of the steepest slope, and then the size of the gradient vector, the magnitude of the gradient vector, actually gives you what is the steepest slope. So 2 pieces of information hidden in the vector. It's like which way should I face to go the most uphill, and then the size of it is what is the slope of that uphill. So let's try that in a couple of examples. I'm going to do 2 examples of finding the gradient. One is sort of like a basic introductory example, and then another one in a word problem. So here is a 2-variable function. This says find the maximum value of the directional derivative. Now that might sound a little confusing, but maximum value of the directional derivative, like that phrase, is exactly what we mean by gradient. The directional derivative says find the slope in any given direction. The gradient says you give me a point and I will tell you which direction to face so that you're going the most uphill. And the gradient is just a vector made up of partials. So the partial with respect to x, which in this case is just 2x e to the y, and the partial with respect to y, which is x squared e to the y. Now this gives us a particular point. So this gives us the point -2, 0. So just to clarify what we're doing here, we've got some function. It's a 3-dimensional picture, really, but I'm going to imagine that the z direction comes out of the paper toward you, so I'm not going to draw it. I'm standing at this point -2, 0. I'm standing on this weird function, and I'm saying, which way should I walk so that I go the most uphill? So I'm saying, like, well, should I walk this way? Should I walk this way? Should I walk this way? This way? I don't know where to go, but I want to walk the most uphill that I can possibly walk. And the gradient is going to tell me which of those directions is the correct direction, because otherwise I'd have to check infinitely many directions, and I don't have time for that. So let's plug in -2, 0 into this function, and it gives us the vector -4, +4. So that tells us if I want to walk the most uphill, I'm going to walk 1, 2, 3, 4 this way, 1, 2, 3, 4 this way. I'm going to walk in this direction. So this is the gradient of f. That is that vector, the gradient of f. But the thing is, that doesn't give us really any of the information. It doesn't answer the problem for us, because this is saying find the maximum value of the directional derivative. Well, that should just be a number. And I didn't just get a number, I just got a vector. So the maximum value of the directional derivative is just the size of that vector. So if I'm finding the size of the vector, I just square each component. So -4 squared gives me 16, and then 4 squared gives me 16. So this becomes the square root of 32, or in other words, 4 square root of 2. And then when it says find the unit vector in the direction, so now I want to say, like, not this big vector, I just want a unit vector in that direction. So here's the biggest slope that I can possibly find. Got that. Now I just need to say which direction is it, and I just want to give a unit vector. Well, I've got the direction here. I just need to scale it down to make it a unit vector, and to do that I just scale it down by this size that I just found. And then 4, the second component, 4 root 2. So this becomes, you can rationalize your denominators if you want to here, but I'm not going to. There's my unit vector in the direction that it occurs. So I'm standing at this point, I'm saying I want to walk the most uphill. Which direction do I walk? And someone would say, this direction. Here's a vector. Walk this direction, and this is going to be your slope. This is the biggest slope. This is the direction to achieve that slope. So that's what the gradient does for us. It just tells us where's the highest, the steepest slope on our function and how to get there. So, sorry to keep checking this. I've just done this lesson like 3 times now. So the last part of this, the last example here is sort of an applied example, but it's the same type of thing. So I'm going to draw a picture as I go. A heat-seeking particle is located at the point 2, 3 on a flat metal plate. So 1, 2, 1, 2, 3. Here's a heat-seeking particle. It's on a flat metal plate whose temperature at any point is given by this function. So this particle can travel around, right? And it wants to find, I mean, it's heat-seeking. It wants to find the most heat that it can find. Find an equation for the trajectory of the particle if it moves continuously in the direction of maximum temperature increase. So this phrase is important. Maximum temperature increase, that means the maximum slope of our temperature function. In other words, the gradient gives us that maximum slope. That's exactly what the gradient is good for. It gives us that maximum slope. So let's find the gradient of our temperature function. That'll tell us where to go. So let's see, the partial with respect to x is just negative 16x. And then the partial with respect to y is negative 4y. And I actually have a point here, right? I'm at the point 2, 3. So when I plug that in, I get the vector negative 32 and then negative 12, which is really big for me to put on this picture. So I'm actually going to scale this down. I'm going to divide both of these by 4, which doesn't do anything to the direction here. It just tells us, it just gives us like a smaller vector to look at. So I'm going to make a few more marks on this and then kind of see where this is. So if this heat-seeking particle on this function is doing what it's supposed to do, it's going to walk over 1, 2, 3, 4, 5, 6, 7, 8 steps to the left and then down 3. So here's its trajectory. It's going to go like this. It's going to go like that. That's what our heat-seeking vector would do. And the way that we found that is with the gradient. That's going to give us the biggest heat increase, is walking in this direction. So at this point, you've gone through probably a lot of these problems. I think we've gone through up to like maybe 13 or so, or maybe 12. So yeah, up to 12. Numbers 12 and 13 are just asking you to find directional derivatives, and both of these are already unit vectors, so just the nice directional derivative formula. Number 14 is a little bit different, because one thing to note here is that this is not a unit vector. So be careful here, because you have to scale that vector down because it's not a unit vector already. So just be careful with that one. Don't use the wrong vector. And then numbers 15 and 16 are asking you to find gradients. It doesn't give you a point, so your answer will sort of be like a vector function, which is fine. So find the gradients of that, and then we just have one more section to talk about, which is optimization. And we've already kind of done that a little bit with the gradient, finding the maximum or minimum value of something. That'll be part 4 of the video, and then we're done with this session.